All right. Hi, everybody. Welcome back for Lecture 7 of the Algebraic Geometry Seminar. Um, Today we are talking about rational maps and blowups of varieties, specifically the blowup at a point of a variety. We'll just go ahead and get into it. There are some minor changes to, if you're following along, how we're running this. Mainly, I'm taking a bunch of graduate courses this semester, and so I don't have time to tack everything up in my notes. So I am handwriting them, which means that they're not accessible in the overlay file, but maybe able to post pictures of my notes in there. So it'll be pretty much the same as what I read in there. Okay, so a few lectures ago, so recently we've been talking about affine schemes, and we will get back to scheme theory soon, but this is just kind of a lecture that you need to have before you talk about the rest of stuff related to schemes. You need to know about rational maps, and it's kind of an awkward thing to just inject into a course, but I feel like there was kind of a natural ending with schemes where we left off, so I'm going to move on to rational maps and then back to scheme theory. So we talked about morphisms of varieties as regular maps, so polynomial functions defined everywhere in each coordinate. So you can have a map from V to W, where V and W are varieties, where locally you can have functions viewed as rational functions, with the denominator not vanishing. And so the idea is that we can pick, for any point in a variety, a representation of our function on that point. So this is a regular map. Now, these are nice, but they're rigid objects. And so what we want now is we want something that doesn't have to be defined everywhere, so that if we have something like a poorly behaved point, we don't have to include that in our notion of the geometry of the space. Or maybe we can work around it or resolve it in some kind of way. And that's actually what we're building up to. Okay. So yeah, sometimes we want to avoid sections of like a scheme. This is also a way of doing that, so you can build rational maps from a scheme to a scheme, and it's going to work somewhat similarly. They're just maps in the structure sheet. So a formal definition of a rational map is to let V and W be varieties, and let U be a Zariski open set in V. Then there exists a rational, well, we can define a rational map phi from V to W to be the data U and phi restricted to U. Where phi U from U to W, certainly injective, not necessarily surjective, is regular. i.e., for every point in U, there exists G and H with phi on U equal to G over H non-zero. U. We will identify rational maps together if they agree on overlaps. So namely, if we have two rational maps, U with phi U and V with phi V, we'll identify them if and only if phi U is equal to phi V on U cap. Okay, so this is the formal definition of a rational map. We say that a rational map is dominant rational map if and only if its image I use dominant if its image is dense in the target. So again, rational maps are going to be our version of morphisms of varieties that aren't defined everywhere. And dominant rational maps are going to give us a proper morphism of this category so that we can have varieties with dominant rational maps as a category. So as an example, we will consider the affine plane, and we're going to define a curve on the affine plane. Y squared is equal to x cubed, that's x squared. So this is going to be our nodal elliptic curve. Locally, this is going to look something like this. And what we'll have is that at 0, this curve is self-intersecting. And so the motivation is we want to do something about this that allows us to identify the multiplicity of the intersection at the origin. And the way we'll accomplish this is with a particular rational map that we'll talk about more generally afterwards. Okay, so what we're going to do is first we will attach a copy of P1 by the idea that at 0 we want to pull apart coordinates in the affine plane. So what we'll have is that if we have coordinates x and y, which can both be 0, then we'll need to attach coordinates a and b projectively that can't both be 0 at the same time. And we'll attach this by saying that xa is equal to yb. And what this really gives us is that if a is 0, so this is on the U1 subset with respect to affine slicing. If A is 0, then we have that Y must be 0, and B is in the units of C. Similarly, if B is 0, then X has to be 0, and A has to be in the units of C. Now, practically, what we can do is we can consider up to scalar quantities the slice that looks like dividing by A. So B over A, and we'll call a new variable P this P over A, and this is going to be on the slice where A is 0. So if A is non-zero, then we have that it's in the group of units, and B can be 0 at the origin. So what we're going to do is this effectively gives us that y is equal to xt. Did I do that backwards? I might have done that backwards. So if we're dividing by a, yeah, I did that backwards. Okay, consider the other slice. A over b, 1, t is equal to, there we go. And now we have it on b, 0. Okay, so now we have this equation defining this property. We're going to say that y is equal to xt. This gives that our equation is now x squared t squared is equal to x cubed plus x squared. So x cubed plus x squared minus, or x squared times 1 minus t squared is equal to 0. Well, we can again pull out this x squared piece and get that x plus 1 minus t is 0. Now in this case, we have two separate curves defined. So we have the curve where x is 0, but we also have the curve where x is equal to t squared minus 1. So what we've done is we've taken our curve on our affine plane, and we've sent it to this new thing where we have a few things going on. We have the exceptional curve, which is the technical word, the exceptional curve x equals 0. And then we have its proper transform, which is this x is equal to t squared minus 1. So this is kind of important that we make these the x and t plane versus the x and y plane. But we have this parabola, and this is minus 1, this is 1, I guess 0, 1, and this is negative 1. Okay, so what we've done is we've taken our curve, and at x equals 0, along the origin, we've separated it into its two multiplicities of intersection. So this rational map, what it does is that it identifies along this point in the affine plane, any curve passing through it will have tangent directions identified by this map through P1. So namely, the tangent direction with respect to one pass-through up to orientation is going to be 1, and it's going to be minus 1 in the other direction. So this is a special thing called blowing up. So this is the blow up of the affine plane at a point, and this is the example provided in Hartshorne chapter 1. Blowing up at a point is a tool that we can use sometimes to smooth out nodal points or singularities of a curve. It's worth noting it doesn't always smooth out everything, but it does best. And we'll define it later on for schemes as well. But that's a little bit more complicated, so we're going to stick with this for today. Okay, yeah, so blowing up at a point looks like this. The more general form of the blow up point, so the blow up is a rational map, and in fact it has a continuous inverse that is also rational, so we call it a birational map. So definition, a rational map by the W is birational if there exists a psi from W to T which is a rational inverse of, i.e. the composition of the functions is the identity on its respective source coordinate. Okay. Yeah, so from this, we can say that, it's maybe an exercise to the viewer to define an inverse of this rational map. But we have that our curve C is birational to its blow up at the origin. So the idea is that we're not losing any geometric information here. We'll make this kind of clear soon. You can identify this as either a birational map by finding the inverse, or soon we'll prove something that allows you to identify this as an isomorphism of coordinate rings. That's often the approach that you want to do, unless you really like constructing these sorts of things, in which case it's kind of fun. Okay, so the general blow up is going to look like putting together a few pieces. So the idea is that for some variety x that is living over your copy of an, we can attach to an a copy of p n minus 1. And so over an, we have now a p n minus 1 bundle living, and we can inject x into this an cross pn minus 1. Now, we have a rational map to an, and if we blow up at a point, call it p in an, the blow up at p is exactly the information of the closure of phi inverse. to get a general P, you just do a base change of coordinates. So you just do some linear transformation on the affine plane, and this is well given by some GLM. Okay, so this is the general blow-up. Important things to know about the general blow-up. There's really two pieces of it. So piece number one is called the exceptional divisor. This word divisor is a technical word. We don't throw it around lightly. We're not going to talk about it right now, but we'll talk about it in a few lectures when we start talking about line bundles. We'll have to talk about a few things like quasi-coherent fields versus films. The second piece is called the proper transform. So the exceptional divisor is exactly this inverse image of the point. The proper transform is the rest of the space, the inverse image of the rest of the space. And so largely the proper transform remains the same. That's the thing that works the way that you're used to. And then the exceptional divisor is kind of the thing that you're working out. In particular, this orange piece here is the exceptional divisor because it's the inverse image of 0 in the plane. And then this blue curve away from the orange line is the proper transform. Okay, so this is a blow up. One thing that we care about in general with blowups and more generally with birational maps are invariants of these maps. So we want to know what we can identify about two varieties being the same if they're birational. So in the same sense that they're invariants of isomorphisms, we want an invariant or multiple invariants of birational maps in this category of varieties with dominant rational maps. So, we will establish a few theorems. One thing that's cool that we'll prove by the end of today is that any variety is birational to a hypersurface. That's kind of a neat proof. And then we'll just go through a bunch of examples of birational maps. And then we'll talk briefly at the end about a condition for what it means for a curve to be singular at a point. Some would argue that maybe that should go first. But I think really the idea of a singularity is that a curve is poorly behaved at a point. So if it's self-intersecting, you can't really define, like a tangent space at that point. If it's cuspoidal, you can't define a tangent space at the point. Nothing has really changed from calculus except for that in the projective closure of an affine curve, you don't have things going off to infinity. You just have things going to some other projective point. Other than that, the idea is really the same, but we will formalize it at the end. Okay, so theorem. This is from Hartshorne. I don't have the number. I should have the number, but I don't have the number. So if x and y are birational varieties, the following are. So the one will exist open subsets, Zariski open subsets of each, with u isomorphic to v, and then with coordinate, with rings of regular functions isomorphic as k attributes. And let me specify that that's an isomorphism. Okay, so for the proof of the first one, we're going to let phi from x to y be our birational map with inverse, phi inverse, which we'll call psi just for the sake of convention. Psi from y to x, birational maps, which are mutually inverse. So then to phi we can associate over u, u with phi of u for any open u in x. And similarly we can associate to psi v with psi of v. Well, we know that their composition is going to look like psi composed phi is going to map to psi inverse of v locally with the composure or with the composition psi phi. But practically speaking, this is the identity, and then this is going to just be u, right? No, this is not going to be u. We don't know that yet. That's what we're trying to show. Psi inverse of v with the identity. Similarly, the opposite composition is going to give us psi inverse of u with composition so. And so then we'll take our open sets that are isomorphic, not to be specifically u and v, but rather phi inverse of v and psi inverse of v. And since the respective rational maps are the identity, then we have an isomorphism of these open subsets. So in this case, u and v, as stated, are not the isomorphic open sets, but rather these inverse images are. Okay, so 1 is proved. Let's prove 2. Okay, so to have 1 implies 2, we're going to recall the definition of the function field on variety. K of x is going to be the set of open sets u and morphisms f, where f is a regular function on u. And it's going to be modulo this identification that u and f are identified with b, g, if and only if f is equal to g on the intersection points. Okay, so these are rational functions. Since we have an isomorphism of u to v from part 1, then we can create transition functions to on intersections, basically to extend their function fields one function at a time. So essentially, for a birational map x to y, we can take on intersections these locally regular, locally rational functions, and we can transition them into each other. And as long as these transitions agree on each intersection, they agree in the image of their intersection through the rational map by the homomorphism property. So essentially, by definition, the function field is naturally isomorphic if the two varieties are birational. I'm not writing a lot here. That's because I didn't write a lot last night. But hopefully what I said is good enough. Okay. So this is a cool theorem. Now we have some birational invariants, and we have kind of some useful lemmas. I really take 1 as more of a lemma, because that really is the thing that proves 2. Okay, so yeah. A particular interest of algebraic geometers is to deal with hypersurfaces of varying degree. What we want is to be able to take a variety and make it birational to a hypersurface. And the idea of this construction is, and this is one idea of the construction, is like with the blowup, you're thinking of a variety that may be singular at some points or along a curve, and you're going to want to just take the sections away from those points or that curve. And that's what rational maps allow us to do. And birational invariants give us practical ways to do that, move these things around. Okay, so I'm going to erase this and just kind of start here.
Tim,
Yes?
first one really you're proving 2 implies 1, right? proving the following are equivalent.
First one, I'm proving 2 implies 1.
And then secondly, what's the implies 2?
I don't think I used the second one in the proof of 1. The proof that, I guess, that 2 implies 1 is that really 2 implies the if. So the way it's stated in Hartshorne is that if 2 varieties are birational is equivalent to these 2. So they're
okay.
Yeah. Yeah. And the reason why I didn't include that 2 implies 0 is that it's stated by Hartshorne as by definition. So yeah, but good catch. Okay. Any other questions, comments, concerns up to here? Awesome. Okay. So proposition. Any variety X of dimension R is birational to a hypersurface in PR plus. So this proof requires an algebraic background that I don't want to assume from viewers, so I'm just going to state some things from like a second semester course in algebra, undergraduate. Okay, so recall that if K is a field, definitely an algebraic first one, then a separable extension. L over K is a field extension, meaning that K is a subfield of L, such that for all alpha in L, which are algebraic over K, the minimum polynomial F associated to alpha in L over X is co-prime to its formal derivative. Okay, so the idea here is really that the minimum polynomial should have distinct roots. So co-prime to its formal derivative implies distinct roots, and that's something that typically you prove at some point. Oh, someone is trying to join. Okay, but yeah, so co-prime to derivative is equivalent to distinct roots. One thing that's an example of this is Q extended by the square root of 2. So namely, square root minus 2 has distinct roots. And is co-prime to X. So yeah, this is a separable extension. Okay, we say that a field extension K over x1 through, we'll say x, I don't use rs, to xs over K has the xi as the transcendent space. Transcendence base of the extension. And so now that we have these kind of background definitions, I think there shouldn't be any words that are left unclear in the proof, and we can prove this. Okay. All right. So, we know that the function field, I'm not going to denote with these capital letters, so let me, yeah, all right, and I haven't said it anywhere else. So this capital K is going to mean function field over the variety X, and I'm going to try and write like curvy X's for my transcendent spaces, but if it's ever unclear, please let me know. We know that the extension of the function field over K is finitely generated. This was proven earlier on in the course. And then since K is its own algebraic closure, we know that it's separately generated. And sorry, K of X is separately generated. Namely, for the polynomials in defining X, we can find maximal ideals that help us cut this out. Okay. So then we can say that there exists a transcendent space for the extension x1 through x. Okay, we are using R, good. K x. Parentheses here mean that these can be rational functions. So just a note about the difference between brackets. No, this does not mean that. If I ever write little k lens x, that means rational functions. These are just functions. Okay. And then this is a finite separable extension. Now there's the there we go. I knew that was it. This is going to be a finite separable extension. Equivalent to the function field. And these do mean now rational functions in these variables. And these variables are functions in K over X. Okay, so we're going to take as a fact from Hartshorne. This is 4.6a, the theorem of the primitive element. We're going to say that if K has an extension L, which is finitely separable, then for any alpha, and then there exists, sorry, alpha in L, which generates L as an extension of K. Now this is a big deal because if we have a transcendent space, B1 through BR, B for transcendent space, for L over K, then what we end up getting is that this alpha is exactly a linear combination of some CI of A. Okay, so I think pretty clearly we can see how this applies. We have the exact premise, and now we have our transcendent space, and so we're going to pick some alpha so that we have a linear combination equal to alpha generating our function field. We're going to call this alpha y, because that's what Hartshorne does. So there exists a function y in k over x with the function field of x, sorry, that should be capitalized, function field exactly equal to k join x1 xr, and this y, which is our alpha. So since y is algebraic over k, it satisfies some minimal polynomial. Rational coefficients in the function field. And by clearing denominators, this is irreducible. And it's going to look locally like namely, this is a one-curve demand on our space. So regardless if this is starting in an affine, AR plus 1, or some PR, this is going to be codimension 1. And then from our codimension 1 constraint, its projective closure, regardless of if you start out affine or projective or quasi-projective, its projective closure has to be a projective hypersurface. So we're done. Okay, so yeah, this is kind of our big theorem from today, is that any variety x of dimension r is birational to a projective hypersurface in PR plus 1. But because we have 22 more minutes, I'm not done yet, and thankfully I prepared some examples of other birational maps. And then also we have that thing about the Jacobian. So, any questions, comments, concerns about the proof before we move on? Okay, cool. So let's go through some examples and let's talk about the Jacobian criterion for singularity. So, examples of birationality. Okay, so our first example is the Veronese map. We talked a lot about this last semester at the start of things. So VD from Pn, P n plus d, choose d minus 1, where we send essentially curves of degree d to hypersurfaces in linear hypersurfaces in this P capital N. And I'm just going to call this exponent capital. What we practically do is we send x naught to xn to all of the possible products of degree capital N. So all polynomials of degree capital N. I don't think anybody who's written a textbook about this has successfully found a way to put this in notation. So I'm just going to write that. I'm not going to be the first. Okay, so this is birational. Hopefully it's not too hard to believe that, in particular because we don't have points that we need to really avoid. Okay. The Segre map, so our version of the tensor, I guess Segre embedding. So this is actually really great. This is not only birational, this is an isomorphism. So what this is it's sigma from, I guess, maybe sigma mn, pm cross pn to pm n plus m plus n. And what we do is we send, this one's also kind of hard to write out. I'm going to do an example with P1 and P1 cross P1. And then this will inform what you think of this map. P1 cross P1 to P1 times 1 plus 1 plus 1, P3. What we're going to do is we're going to send A and B as points in P1 to A tensor B. And so practically, if we choose coordinates x naught, y naught, and x1, y1, this is going to map over to their tensor product, which will look like x naught, x1, x naught, y1, x1, or y1, y naught, there we go. Y naught, x1, and y naught, y1. This is the Segre gap. This is also birational. This is an isomorphism. And yeah. Okay. More examples. We have that the cuspidal. Oh yeah. So we say, I guess there's a definition here. Hiding. So a variety Y is called rational if it is birational to Pn for some n. So the Veronese map is certainly birational, certainly rational. The Segre map is certainly rational, at least over its domain. If you have a curve cutting out all of Pn, then that would be a rational variety. Okay, so an example of a rational variety besides these two is the cuspidal cubic. So y squared is equal to x cubed. That looks locally like this. So this is birational, essentially in the same sense of the blowup that we computed earlier with y is equal to tx. It works similarly, but you do have to just shift over a little bit so that your exceptional divisor gets on the right-hand side. This is just if you want to work this out at home. Let's see. The plane Cremona transformation is a very interesting one. Plane Cremona transformation. This is a birational map from P2 to P2. And it's interesting more that this is its own inverse. So what we're essentially doing with the plane Cremona transformation is we're taking the projective plane and we're blowing up at 3 separate points at once. But we're not doing it the first time we applied the plane Cremona transformation. We're doing it the second time we applied the plane Cremona transformation. And so it has the same geometry as a blowup. But this is something that people used to do back before blowups were really popular. This was a map that could blow up the plane at 3 points. Okay, so how does this map work? What we do is we send our 3 coordinates, x naught, x1, x2, over to the product of whichever index is not that slot. So if this is 0 and this is 1 and this is 2, then we would have x1, x2, x0, x2, and x0, x1. So clearly this is defined away from any point where two of these are 0. So namely, this is not defined on the hypersurfaces 0, 0 to 1, 1, 0, 0, or 0, 1, 0. Right? But then it's its own inverse. So the idea is that if you compose this twice, then what you get back out is, well, we're sending, say, by splitting, it's going to send x1, x2, x0, x2, x0, x1. This is going to get sent over to x0 squared, x1, x2, and then x1 squared, x1, x2, and then x2 squared, x0, x1. But since this is a projective point up to scalars, we can knock off this 2, and we can knock off the respective linear indices, leaving us back with x0, x1, and x2. So it's its own inverse, and then if you're taking these 3 points in the plane as your singular points, you're effectively blowing up at these 3 points back to your ordinary projective plane. So this is kind of like a cool classical geometry thing. Okay, so these are my examples of birationality. One final thing that we're going to talk about in the last couple minutes today is what a singularity really is in the projective geometry sense, and what the Jacobian condition is for singularities. Any questions about what was presented so far? Okay. So, singularities. All right. So, definition. If we say that a variety V is the vanishing of some polynomials F1 through Fr contained in Pn or An plus 1, not that this is really, it'll make sense. We say that V is singular at a point P, I'm going to call this space X. In X, if the Jacobian has rank dimension at P less than expected, so less than R. So what is JP? Well, JP is going to be the matrix partial derivatives where each vector is the partial of the function with respect to the xr, not r, xnth derivative, and then each respective column just changes which function you're taking the partial of. This one. So this is the Jacobian rank condition on singularities. As an example of a singular curve, we have our cuspoidal cubic. So this is cut out by one equation. We would expect that it would have rank 1. It's partial, so if we say that f of xy is equal to y squared minus x cubed, well, it's partial with respect to x is going to just be minus x squared, partial with respect to y is going to be 2y Well, since we have a y term and no constant linear combination, we can see that at 0, J0 is going to be exactly a 2 by 2 matrix, 0, 0. This has rank 0, which is less than 1, which is what we would expect from cutting out one equation's worth of data. So this is what a singularity is. This is why we have things like rational maps and blowups. We've computed some examples of how to resolve simple singularities, like nodal or cuspoidal curves. And we've maybe made the very important observation that it doesn't always work for more complicated things like blowing up a long curve or something. And yeah, next time we will be back. I think in the syllabus I had said something along the lines of doing rational maps and blowups of schemes. That's more complicated. I don't think I want to do that next. So we're going to talk probably about quasi-coherent sheaves. Thank you for your time, and I'm going to go ahead and end the recording.